Hello everyone, and thanks for watching Edupedia World videos. This is the second video for the topic Kinetic Theory of Gases. In the previous video, the last thing I did was tell you the assumptions in Kinetic Theory of Gases, and now we'll move on to actually analyzing the motion of a gas in a box. We'll consider a cubical box of length L length, width and height L. Let's draw the axis. This is the x-axis, this is the y-axis, and this is the z-axis. And let's take a particular molecule which collides with this wall and moves away. We know that the collision is completely elastic because that was one of the assumptions. So if this angle is theta, this angle will also be theta. Let's say this is a velocity v, which had components Vx, Vy and Vz. What happens after the collision? The y and z component of the velocity remain the same, whereas the x component of the velocity is reversed because the line perpendicular to this wall is in the x direction. So finally its velocity becomes minus Vx, Vy, Vz. So the change in velocity is minus 2Vx, and the change in momentum delta P is minus 2mVx. Again, remembering our earlier convention, small m is the mass of a single particle, and right now we need the mass of a single particle. Right. So what is the force on this ball? That would be delta P by delta T, where delta T would be the duration of the collision of this ball. However, since we are not just studying this particular particle, we are studying a huge number of particles. We need to calculate the average force exerted on a particle, or rather by Newton's third law, the average force exerted on a wall. So the average force exerted on a wall will be the same momentum change divided by the change in time. However, the time will be the frequency of the occurrence of collisions. So let's say this particular molecule goes like this. It goes here and then goes here, goes back here. We can't really visualize the z direction, that doesn't matter, and then goes here. Right. So how much time did it take? The y and z components of velocity doesn't matter. The x component of the velocity is minus Vx, and after it collides here, it becomes Vx again. So the total distance traveled in the x direction is 2L, and the velocity is Vx. So the time taken will be 2L by Vx. After every 2L by Vx seconds, this molecule will collide with this particular wall again, right, whatever Vx may be. So the average force exerted on this wall by this single molecule will be delta P by delta T. Now delta P is minus 2mVx for the ball because its momentum is changed in the left direction. So delta P for the wall will be 2mVx. So the force exerted, average force exerted by a single molecule on a wall will be 2mVx by 2L by Vx, which comes out to be mVx squared by L. So this is the force due to one molecule. What is the force due to all the molecules? We just add them up, right? And the sum will come out to be over Vx because m we assumed is the same. That is, we've assumed there only to be one gas, so the mass of each particle is the same, right? So from this we get the equation that the force exerted on a single wall, remember this is on one wall, this is equal to m summation Vx squared by L. Now this is not the sum of Vx whole squared, this is the sum of the square of each Vx. Vx1 squared plus Vx2 squared plus Vx3 squared and so on. Right. Now I'm going to introduce a little concept of statistics which is called the root mean square speed. It's possible you've seen this in chemistry, it's possible you haven't. Right. So root mean square is another way of calculating the variance in a particular sample of data. So let's say you have n1, n2, n3, n4. N average is defined as n1 plus n2 plus n3 plus n4 by 4. Right, so this is the average of n. There is another quantity called the NRMS. RMS stands for root mean square. And it is useful when one of the times it is useful is when n have different signs, as in this case Vx might be positive for one, Vx might be negative for another, so average of Vx comes out to be 0. So and a solution to that would be the average of the magnitude of Vx, but an easier solution to that is the average of the square of Vx, because the squares are always positive. So NRMS is, just go by the name, that's how I remember it, root mean squared. So first it's the root, then it's the mean, that is divided by 4 of the sum, then it is the sum of the squares. So n1 squared plus n2 squared plus n3 squared plus n4 squared. Right. So this is just the definition of root mean squared. Just like there's a particular quantity called the average of a certain number of quantities, there's another quantity called the root mean square of the certain number of quantities. Right. So let's multiply this upper equation by capital N and divide it by capital N. Capital N is the number of particles. Right. Remember our conventions. So summation Vx squared by N becomes m n by L V RMS squared. Right. Sorry, summation Vx RMS squared. Right, because right now we've only done for x. So I'm running out of space, sorry. So we've gotten to the part where the force is equal to small m capital N by L Vx RMS squared. Now what is Vx? Remember, n RMS squared will be the sum of these by 4, right? This is root mean squared, right? So Vx RMS squared will be equal to Vy RMS squared, which will be equal to Vz RMS squared, because of our first assumption in kinetic theory that all molecules move randomly in all directions. So x, y and z directions are completely equivalent. However, the sum of these will be VRMS squared, because V squared is equal to Vx squared plus Vy squared plus Vz squared. So the sum of these three is equal to VRMS squared, and each of these three are equal. So from this we can get that each of these three is equal to a third of VRMS squared. Right, because all three of them are equal. So from this we get this is 1/3 of mn by L VRMS squared. Right, so this is the force. What did we want? We wanted the pressure on a particular wall. The pressure is forced by area. What is area? Area is L squared. So that means the pressure on a particular wall will be 1/3 mn by L cube VRMS squared. But m is the mass of one particle, n is the number of particles, L cube is the total volume. So this becomes the total density of the gas. From this we get our first important relation, P is equal to 1/3 rho VRMS squared. So we see the result, which should have been sort of intuitive to us from the start, which is the higher the speed of the molecules. Remember, VRMS is the measure of the speed of the molecules. If molecule by a certain amount, the RMS speed of the molecules would also increase. Right? If we decrease the speed of the molecules, the RMS speed will decrease. So RMS speed is a measure of the average speed of the molecules, except like we said, the problem comes in two places. One, the average velocity would be 0, and second, there's a square in this equation, right? So we need the average of the squares. That's why the concept of RMS comes up. Right. Now I'm going to just start with this equation. P is equal to 1/3 and I'm going to write it in a number of other ways which are generally useful. Right. So from this, one way is PV is equal to 1/3 m VRMS squared. Again, remember our notation. M is the total mass of the gas, V is the total volume of the gas. Right. PV can also be written as 1/3. M is the total mass. It can be written as two number of ways. Mass of one particle, number of particles. or mass of 1 mole, number of moles, right? So all of these are equivalent. The only difference is we multiply the mass of 1 by the number of 1, where 1 can be 1 particle or 1 mole or the actual mass of the gas, right? Now we already know the result. PV is equal to small n RT, and from this we get PV is equal to 1 by 3 m naught Vrms squared. From this we get Vrms is equal to root 3 RT by m. This is a very important result because R is a constant, and for any gas m naught will be a constant. Remember now, m naught is the mass of 1 mole. You remember I just showed you this equation in the previous lecture, said I'll derive it, and then often you'll be confused what should be here. Should be the total mass or the mass of 1 particle or mass of 1 mole. It's m naught, so it should be the mass of 1 mole. Right? However, just a little trick, this is actually also equal to root of 3 kT by small m. Because small m is the mass of 1 particle, m naught is the mass of 1 mole, they are related by the Avogadro's constant, and inversely R and K are also related by the Avogadro's constant. In fact, every equation which a physicist describes to you in terms of 3 kT by m, a chemist will describe to you in terms of 3 RT by m naught, because when we are dealing with actual experiments, it is easier to talk about moles than actual particles. But m is the mass of 1 particle, and the way I remember it in this formula, the mass of 1 particle is very small. K is also very small, so they are together. The mass of 1 mole is a regular sized quantity. R is a regular sized quantity, 8.314. So they are together. Right. So now that we know Vrms, let's try to calculate the relationship between temperature and kinetic energy. Right. This shows us, first of all, this shows us that temperature is indeed proportional to the speed of the molecules. If the molecules start moving faster, Vrms will increase. That means the temperature will increase as well. So this sort of explains to us why a hot object and a cold object, when they are kept in contact, the temperature decreases of the hot object and increases of the cold object till they become equal. Because the hot object has molecules which are moving faster than the cold objects. Due to collisions, the hot objects transfer some of their momentum to the cold objects, which increases the Vrms of the cold objects, thus increasing the temperature. Right. So now that we know Vrms, let's see what kinetic energy does. Kinetic energy is basically summation half mv squared. M is the mass of 1 particle, v is the speed of 1 particle. Right. That can also be written as, by our own definition, half capital M Vrms squared. Right. M is the total mass of the gas. Right. But we know that PV is 1 by 3 of the 3 Vrms squared. So from that, half m Vrms squared will be 3 by 2 PV. From that I get kinetic energy is 3 by 2 PV, which is 3 by 2 small n RT. This result was the first major success of kinetic theory of gases, because it quantitatively shows us the total kinetic energy of a particular gas. That means the sum of the individual kinetic energies of every molecule is linearly proportional to the temperature. If you double the temperature, again, just a reminder, every time we say temperature, we're talking about Kelvin because that is the standard unit. If you double the temperature in Kelvin, then the total kinetic energy of the gas has to be doubled. Right? This is the first major success, and K is also denoted as U sometimes. The total internal energy of the gas. That means the total internal kinetic energy, because we've ignored the total internal potential energy. If you remember, we said that all the interactions between molecules will be neglected. Right. So this finishes the specific topic of kinetic theory of gases, but there are a couple of other related topics which are very important, and so you need to know. The first of them is the concept of equipartition of energy. Now we'll deal with this topic again in a later chapter in specific heat capacities of gases. And also, I don't really like teaching this topic because there's nothing to teach. I'm just going to tell you a principle. You're hardly ever going to use it, and you're going to prove it if you take physics once you get to college. But everybody tells us it's important in the course, so I'm just going to state it. The concept of equipartition of energy basically states that for every degree of freedom. Now, okay, first let me explain what a degree of freedom is. If a molecule can move in 3 separate directions, x, y, and z, so this is inside, that means it has 3 degrees of freedom, which means that to represent the molecule correctly, you would need 3 particular coordinates, right? X, y, and z. So if a molecule is on a plate, if we take a square plate and put an object on it, that object will have 2 degrees of freedom if we constrain it to stay on the plate. So it is sort of the number of independent ways you can move. So 3-dimensional free object has 3 degrees of freedom. The equipartition of energy states that, and it is actually a very fundamentally important concept in statistical mechanics, but you don't really realize the importance of it unless you start reading further in advanced physics. So the average energy of a molecule in a gas is half kT for each degree of freedom. Now right now we are just using a simple gas in a box which has 3 degrees of freedom, but in a later chapter we'll see different degrees of freedom. Then this will be more important. Right now all it says is the average energy of a molecule is half kT for each degree of freedom. That means the average energy, or just kinetic energy because we are neglecting potential, is 3/2 kT for a single molecule. Right? For the whole gas, it will be 3/2 kT multiplied by n, which is the number of particles, and you can verify that this is exactly the same as what came previously. So this was basically why kinetic theory of gases was a success, because equipartition of energy came first, and equipartition of energy was considered to be true, and equipartition of energy proved that this should be the result. Using kinetic theory of gases, we were actually able to derive this result using basic Newton's laws of motion. Right, so that was remarkable. You came up to the exact same result by 2 different methods, which show that what we are studying must most likely be correct. The last important topic, which is also similar to equipartition of energy, is important in statistical mechanics. In fact, a very interesting thing I'll tell you is, when you start studying this later on, thermodynamics and statistical mechanics are exactly the same thing. They are so intertwined because thermodynamics is the macroscopic study of the same thing which statistical mechanics is the microscopic study of. So another statistical mechanical ensemble which we see has to do with the Maxwell speed distribution. And if you take this advanced physics once you go to college, you will actually be able to derive this result from equipartition of energy and some other results. Right? But right now I'm just going to tell you, I'm not going to give you the derivation. Maxwell speed distribution, what it tells us is that the distribution of speed in different molecules. For example, if there are 10 to the power 23 molecules, then Maxwell speed distribution will tell us that there are 10 to the power 18 molecules with a speed between 10 meters per second and 12 meters per second. I'm just giving an example. That's what it does. If you give a range of speeds, then Maxwell speed distribution will tell you how many particles are in that range of speed. Right? Before writing the actual function, because it's slightly complicated, I'm just going to draw the graph, because the graph is incredibly interesting. The graph is called the Maxwell distribution curve or the bell curve. It has many other names as well. And that's because this graph is one of the most fundamental graphs in all of nature. And in fact, you can prove with statistical mechanics that anytime you have a truly random process, this will be the graph that will happen. Right? So in this case, it will be speed versus number of molecules, but it could be anything. I'll give you an example. This could be the number of people and this could be the year when they die. Some people die at a very young age, some people die at a very old age, most people die somewhere in the middle. Some people are very weak, some people are very strong, most people are in the middle. Some people are very stupid, some people are very intelligent, most people are in the middle. Right? If you take most random processes in life, the curve will be something like this. Similarly for Maxwell's speed distribution, the number of molecules having a very small speed will be very small. The number of molecules having an extremely large speed will be very small. Most of the molecules will have a speed somewhere in here, and there will be a particular speed which the maximum number of molecules will have. Right? So the structure of this curve is something like dn by n, which is the number of molecules having a speed between n and n plus dn. So if I want 10 and 12, then n will be 10, dn will be 2. But it generally only works for small distributions. Right? So this goes like, I'll just tell you first how I remember it. V squared e to the power minus kv squared dv. That is what it is, right? This is the number of particles, this is the speed. Most particles have a particular speed. A few particles, the number is small, have a small speed. A few particles have a large speed. I apologize for that. Right? So when v is small, v square dominates. This doesn't dominate, this equates to 1. So the curve is increasing. But when v gets large, e to the power minus kv square dominates, so it becomes like this. The actual function is dn by n is equal to 4 pi times m by 2 pi kt to the power 3 by 2 v squared e to the power minus mv squared by 2 kt dv. I'll just write it as f of v dv, where this whole thing is f of v. Now it seems complicated, that's why I showed you this first. This is how you need to remember it. It has to be v square e to the power minus kv square. That is the standard form for a Maxwell distribution. Now kv square has to be dimensionless because it's in the exponent. So to make it dimensionless, you have mv square has the same dimension as kt. We saw that from equipartition of energy. So this becomes dimensionless. The thing here which is kept in front, this is only kept to normalize this function. Normalizing means dn by n gives you the probability, right? So if you take the total probability and you add it up, it has to come to 1. So if you just integrate this particular aspect from 0 to from 0 to infinity, that means speed from 0 to infinity, you will get the inverse of this particular thing. So we add this is the normalization constant, so that this gives us a probability distribution. Right. Now there are some important quantities in this probability distribution. First is the root mean squared. We already calculated it to be root 3 RT by m naught. By the way, this is small m and this is m naught. You can equate them later on. Right? This can actually be derived from this equation. How is it derived? How would you calculate VRMS? It would be integral of f of v times v square dv. Right? It has to be actually by integral of f of v dv. Integral of f of v dv will be the total number of particles. Integral of f of v dv multiplied by v square will be the total number of particles having a speed v multiplied by v square. Right? So it's sort of like taking a weighted average. Except we know that the denominator is equal to 1. That is why this has been normalized. So if you calculate this particular quantity multiplied by v square and integrated, you will need to do integration by parts, I guess. You will be able to calculate this final result. So again, we got this result from two ways. We derived it from kinetic theory of gases, and Maxwell distribution law, which comes from equipartition, also predicts the same result. The other important quantity is V average. V average is nothing but the average speed of the molecules. That will be integral of V times f of v dv. The number of particles with the speed v multiplied by the speed v. Right? If there are 3 particles with 2 meters per second and 5 particles with 7 meters per second, 3 into 2 plus 5 into 7. Here it will be 3 into 2 square plus 5 into 7 square. Right? This comes out to be, if you don't need to integrate it, but you do need to remember the results. This is 8 RT by pi m naught. And similarly you have the third, which is the most probable speed. Most probable speed is simply this speed. The speed which the maximum number of particles have. That you can see easily. How do you guess? The slope should be 0, the derivative should be 0. So it is the v at which d of f of v by dv equal to 0. I'm only telling you the last three things because you need to know, you should know rather, that all these three formulas which you'll remember have been derived from this original formula. V most probable, by the way, comes out to be root 2 RT by m naught. So you need to remember this. V most probable root 2 RT by m naught. Average root 8 RT by pi m naught. Root mean square root 3 RT by m naught. Right, you need to know them, but it's also very helpful if you actually know that they can be derived from this particular Maxwell distribution. Yeah, that completes kinetic theory of gases. Thank you.